Can everyone hear me? Yeah? Yay. All right, we're about to start. Um, so, this talk is going to be about big data. So before I start off with, I've got a quick confession to make. I'm not actually a developer. I'm a recruiter. No, I'm kidding. I can see it in your eyes. That was actually a joke made up yesterday. I'm actually an engineer. And when I am not making bad jokes, I'm normally writing bugs. So, a bit more about myself. My name's Sam. I'm head of data engineering at a company called Big Game Labs. Before that, I was tech lead at PlayStation. And I had a few gigs at like Discovery Channel and Just Eat. Started off my career as a web developer, like a lot of you probably here, doing, front-end, back-end work, doing services, learning every new JavaScript framework every other week or so, standard rate. But then at some point in my career, I was realizing that I was working in a distributed system with microservices that had messaging flying all around, and we weren't utilizing this data. So I kept saying, look, we've got every single customer interaction we have on our system, but we're not utilizing it. So take an example of an e-commerce website. A user or a customer adds a few things to baskets and removes it, then adds another thing, then removes that, and then finally adds one last thing and then checks out. The people who are analyzing this data, the true data governance really, they are only looking at the end state. So they're missing out on all the goodness that event sourcing preaches, which is the journey of how the end state came to be, right? A customer removing a few things from a basket is actually quite intriguing to understanding their behavior and asking why. So based on all this nagging that I was making throughout the team, I was approached by the data engineering team, the BI team, to lead a team to try and get them to become standard data engineering team and implement all the industry best practices that we see day to day and take for granted. Things like testing, immutable infrastructure, metrics, alerting, all the stuff that you probably do day to day, but the data world sometimes in some companies can be quite lagging behind. But the first question I sort of asked myself, which is to change careers. And I think it'd be quite interesting to find out how many of you are data engineers or are interested in moving towards big data or are just, trying to find out what's interesting there. How many here are interested in or have worked with any of the tools? Okay, so not many of you, so it's okay. Everything I say here is correct, by the way. So that's kind of where I was, right? I was scared. I was a web developer doing .NET, and that was my comfort zone. Do I want to move towards this big data malarkey? Really, the reason I changed careers is because at some point I started believing, and I still do believe, that the difference between company A and company B is no longer the tech. It's a factor, but it's no longer, how well you do the tech. It's actually your data, your customer behavior. You've got companies being bought for billions like Snapchat, Instagram, WhatsApp. It's not because Facebook can develop an image filter or a chat app. It's because of how they understand their data. And that's kind of what really convinced me to move. So to start off with, what exactly is big data? And I like this tweet. And this is 6 years ago, right? But it still applies today. And it really lets you know that not everyone says, oh, we're doing big data, but they're doing thousands of records, millions of records. Obviously, we're big data. But there isn't like a categorical answer of yes or no. But there's been now an agreement of what do you define as big data, which is 3 V's, right? The first one is volume. How much data you're ingesting, how much, is it gigs, terabytes, how much actually you're taking in. The next one is variety, which is how many different data sources you're hitting all the different APIs, all the different third parties. And the last one is velocity, how fast this data is coming through. You know, is it once a day? Is it once an hour? Is it once a minute? Depends, right? So it depends on how far. This is where you go towards the streaming world. So throughout this talk, I'll walk you through how we journeyed through building this pipeline and the failures, more importantly, the failures that we face. Because I think we're in a unique industry, and I keep preaching this, which is we learn from our failure. And that's really the beauty of our industry. The first thing I learned was what ETL is, and it's the bread and butter of big data, which stands for extract, transform, and load. Extract being you take it from all the different data sources. Transform means you conform it to what your business understands. So those of you who understand domain-driven design, it's the ubiquitous language. So for example, in naming terms, you call PayPal and it tells you that this is a payment reference, but your company calls it order ID. You don't want your analyst to learn all the terminology from different data providers, so your job is to transform it and get it into a shape that they understand. And finally, you load it into a data warehouse. So the first question I asked myself was, what's the difference? Why do you call it data warehouse? It's obviously a database. You know, why do you want to call it a data warehouse? And actually, there is a difference, which is one is geared for writing, OLTP, which stands for online transactional processing, and the other is geared for analytics, OLAP, online analytics processing. So one is obviously designed to write fast, write a lot and read once, and the other is for analysts reading in. You're more reading than writing. But then, while I was working with the team, they were like, oh, we want to implement a data lake. And I'm like, I just left a JavaScript community that constantly comes up with new buzzwords. Why do you want to move to something else, right? But quickly I found out the pains they were feeling with using a data warehouse, and I'll walk through these pains with you. But basically a data lake is something like cloud storage. Think of it as an infinitely scalable hard drive like S3 or Google Compute or Google Storage or whatever Azure is calling it nowadays. And you store your flat files there and you query them via SQL. So obviously I came in and seen they had a Redshift data warehouse, and Redshift is kind of Amazon's amalgamation of Postgres. And they claim it's like big data scale and it's great, but it's only great if you're normalizing records. Once you start looking at JSON, which is a lot of what the APIs are returning, it becomes slightly more difficult. It is still difficult with Postgres, but it's even more difficult than Redshift, with Redshift. So the state of play where I came into the team was they had this one Windows machine that is the machine to rule all machines, and it had lots of little Python scripts that move data from A to B, A being a database, S3, SFTP, all sorts of places. It gets that data, puts it into Redshift, and hard-coded all over the places. And if that machine dies, you're screwed because it's not in version control. Like it's server, Snowflake servers to the definition. But not only that, it used to fail a lot. And when it fails, it takes 8 or 9 hours to run. That's daily. But when it fails and you fix it, even if you fix it within 10 minutes and you release a hotfix, they're not getting any data for that day. It takes 9 hours to run. So that's the first thing we had to fix, which is get it immutable, move it away from Windows. We get it running in immutable infrastructure. We got a build tool. I think we used TimCity to start off with to run the build. It still took 8 or 9 hours, but that was the very first fix we did. And the next was to try and move it to lower increments, so we fail faster. The problem with that is a lot of the tools that were, or a lot of the components or the services that were calling one of our data sources were doing select star in their queries. So we couldn't just add a timestamp column saying this is the thing that changed because it will break. So we ended up using SQL Server's change tracking control to tell us, like an audit table, to say these are the IDs that changed, and we'd use that as the primary keys to sort of join to find out what changed. Then we found out that SQL Server's change tracking control tells you how long do you want to keep your data, and you say 2 days. And then it says, okay, fine. I'll clean it when I want to. I'll just make sure that you have 2 days worth of data. And we were like, that's okay. The problem is that it can clean up your data whenever it wants. which is it can be done during peak time, which affects the website. So we found that out, and we changed it to audit triggers, and then we have control over when to clean it. But obviously, this wasn't really scalable, so we need to build a data pipeline, right? And we set out set standards of what we're going to build, and how it's going to work, and what it needs to be, how it needs to work, how it needs to function, how it needs to behave with failure, and we have designed failure from the very start. We used Apache Spark as our underlining foundation for two main reasons. One, which we publicized to the business, and two, which we didn't tell them. What we tell them is, oh yeah, Apache Spark's really cool, everyone's doing it, everyone's amazing. So that's the reason we should use it. And also, you can write your stuff in SQL, because we had major pains trying to teach analysts how to write Python or Scala, and we just gave up, because they're like, but in SQL is so much easier. So they can write SQL. It's a data engine. Spark's a data engine. So you can write SQL. You can write Python, Scala, Java, even R for the data scientists. And it will treat it all in the same way and still handle the same data. So it was really powerful, and most people can reuse stuff. And we use notebooks to kind of let people share their knowledge. So it was really good. But the underlying reason is the fact that it's a distributed data engine, and it allows us to handle failures. When one of the nodes fails with data, it handles it underneath the hood. So we never have to worry about that. The end infrastructure, this is how we designed it from the start. It actually looked like that. The main problem with Redshift that they were facing was, even though it was geared towards analytics, it was the single source of failure. So for example, you would have your dashboards running every day, looking at your data warehouse, and they'll be fine, working fine. But then the data scientist comes in and says, you know what, I've got the perfect machine learning model here, and I'm going to build the most amazing recommendation engine to have ever been written. And look, I've got some results for customers on what they ordered, or what they played, or whatever they did. But I'm going to see if this is actually accurate. So I'm going to query all of history to find out what every customer has ever done to see if this engine would have recommended the right thing. What that happens is it will take so much processing power that the dashboards that are crucial to your business don't run anymore, because the data scientist is hogging all the compute. So our underlying problem was storage was very, very tightly coupled to compute. And some data warehouses try and solve this by saying, look, you can assign queues, so only 10% of your processing power goes to these people, 15 goes to that, 30 goes to that. But the problem with that is that's a lose-lose situation. Nobody's happy with just 10%. Like, why? Why? Obviously, my work is more important. So we needed to separate storage and compute, and this kind of gave it to us. All the storage was done in S3, and then we'd have different Spark clusters, EMR, Elastic MapReduce. That's Elastic MapReduce to do whatever you need to do. So that's doing our ATL. That's serving the dashboards. Dashboards are served like things with Tableau or Superset. It would look at that data. That's still on S3, but then the data scientists can spin up their own machine and come up with their own theories, and they will not affect anyone. So this is basically separation from concerns. That's all it is. It's just SRP. That's our end goal. We did end up implementing it, but we had a few hiccups down the road, which I'll kind of share with you. We had to ingest all sorts of formats. The CSV and JSON is what you standard get. People just put some CSV into S3 or FTP. The APIs will return JSON. But when you come to query, or you want to look at a 3 gig file of JSON, you can't really do that in memory. You maybe can if you've got a 32 gig machine, but once it goes up to 30 or 40, it gets very, very, very difficult to manage. So we kind of start looking at Parquet and Avro, which is a columnar storage, just like what Redshift is, and I'll kind of mention what columnar is in a minute, but it's compressed. That's all it is. So it's smaller sizes, so it's easier to manage. And it also comes with the schema. This is basically what columnar is. Traditionally, you store the entire row together, and this is what a traditional database does. But because there are different data types or data formats, one's a string, one's a timestamp, one's an int, there's not a lot of compression that you can do. With columnar, you're storing the data types together per the column, so there's a lot more compression, hence it's faster. Another pain we felt was those traditional Python ETL scripts, all of them were trying to do the management of the queries or the alerting all together in the same time, and it became very, very difficult to manage. So we had another problem of separation of concerns. So that's why we started implementing DAGs. And what DAG stands for is a directed acyclic graph, which is this should run before this, but not before that. And basically, we moved all the scheduling, the alerting, the retrying, the backoff outside the code and into Airflow, which is a scheduling workflow manager. But this allowed us to really easily use something that's industry practice to sort of say, you know, we run A, B, and C before D, but alert and retry if it fails, and back off for a while and alert to, you know, PagerDuty or SQS and something like that. But it's also much more visual, so much more easy to visualize and understand that this thing depends on that. So we moved away the complexity that was within our code to something else. And our code specifically purely focused on the transformation logic and assumed that the data's there. The underlining definition of our data lake was this. We'd get the raw files as they are. Very, very, very small number of providers provide you data in Parquet. Most of them provide you in CSV and JSON. We save it as it is, and then we save it down to, we save the file as it is to Parquet to make it more manageable. We keep a record of the original file. You might think, okay, now that you saved it, you don't need it. But what happens a week later when they delete that data, and then you need to do a backfill? So that's why you need a copy of what they were given. Once you move it to Parquet, it's more manageable. You model it, you transform it, you do your transformation logic, so you get the column names that you want. You join what you need to do. But this last step, this mirror step, is not something that's industry standard. Amazon are trying to push for it, but it isn't. The reason being is after this step, you can start moving data into your warehouse. And traditionally, that's what people did. The ETL that I mentioned earlier, what a lot of people were doing was actually ELT. Because of the fact that they couldn't transform gigabytes of data within their own machines, they would load the extract and write it to the database directly, or data warehouse, sorry, directly, and then they would do the transformation using the power of the data warehouse and then write the results of that onto another table. So everything was done in your data warehouse. With this, you're basically doing your transformations and then writing it down to S3, so it becomes a mirror. So then you're able to get your data scientists to look at the table as it is in your data warehouse, but it's actually in S3. So it's to give us freedom, really. We needed to have idempotent runs, right? Because of the fact that things can change underneath, and the data can change, yes, but you're able to say, if I'm going to run this run, I will absolutely know if I run the same run 3 months from now, it will still work exactly the same way. But everything we've discussed so far is stuff we can do and we have full control of. We have not even mentioned the vast majority of the problems, which is just bad data. You know, your providers will give you something. This thing is supposed to be a timestamp. We're just going to give you a string. This thing is supposed to be an int. We're going to give you some weird Boolean value that's also null. And also things that you can't really handle with a validation, which is we're going to give you a timestamp, but I know we agreed to give you UTC, but actually we're going to give you in British Standard Time, because you can handle it. So we needed some form of validation pre-ingesting, so we're able to die. And then one of the painful things is when they give you a CSV and it's just a simple CSV, and then they'll add a new column, but they won't add it at the end, which is what we agreed on. They'll add it somewhere in the middle. So then, because it's a fat file, you don't know. There's no schema attached to just a simple file. So it's actually quite annoying. So we had to do some form of schema validation, and then oh, that was awkward. So the schema now is attached to our code base, and we're able to validate it every single time. Now every single run gets validated, and that's really, really important. But now we have schema validation. It's on S3. Look at that, we're web scale, right? It's amazing, and we're not even calling Redshift anymore. It's very performant. We need more performance, just add more machine to the Spark cluster. It's perfect. Now that we were using different clusters, we had freedom. We were literally living the life. And then we realized we have a different set of problems, which is corrections. And that's really annoying because you will get into a situation where you get data from your provider and it's all right. But then 3 months later, they will tell you, you said we told you you did 1,000 sales, you actually did 750. And then you're looking and you're like, how do we handle this? All our data is now flat files in S3. It's not actually in a data warehouse. It's not a matter of going there and then deleting, because there's no such thing as deleting when you're doing flat files. If you do it, you break your idempotency rule. So we were like, okay, how are we going to handle this? How are we going to deal with corrections for the feeds that we're told will never be corrected, right? So we come up with this snapshot versus transactional methodology, which is rebuilding. We rebuild something after we were told. We're constantly rebuilding based on new data. And the transactional are for things we'll definitely not get any new feeds on. The problem with that is we started seeing things that we knew cannot be corrected, but they were told it's being corrected because of a bug, a failure, that you didn't get the data. So your data was correct, but it was partially correct rather than wrong. But to business, that's still the same thing. It's wrong data, we have to fix it. So I think one of our biggest feeds was about 100 gigs a day, but we were still able to do it. Within 20 minutes based on our cluster. We had 10 nodes of M4s on AWS. The problem is some of the things like the PS4 events were 1 or 2 terabytes a day. Easy. You can't do that. You can't snapshot them. So it is a compromise. And you're like, okay, with that level, we have to accept some form of corrections. But for event feeds, weblogs, we know it is highly unlikely that there will get corrections on weblogs. And if we do, it is not business crucial where we are providing wrong numbers. That led us to 3 levels of testing, which is the first one, which is a very basic one, but still very, very important, which is your transformation tests. Right? You have 3 or 4 or 5 different feeds, which you are going to ingest to try and build a table. And this table is, for example, adding these 2 columns, subtracting that, multiplying it by currency from another table. And you're able to say, look, I'm going to give you 5 sample fields. You run your transformation logic, and you assert on the resulting column names. And you assert on business-specific terms like, we made X amount of sales. Problem with that is you're only testing your sample data. You're not testing the actual data that comes in. So we're not doing integration tests. We're not even testing the DAGs. You change a dependency, you're not testing that, because your tests assume that the data's there. So we started implementing integration tests where we have Airflow actually build the entire, we have a test that runs throughout the thing. The beauty of that is it made it possible to say, look, the data's in S3. We can have A/B tests. We can come up with 2 different versions of the code and run tests against them and say, look, what would happen? What would the table look like? What would the model look like if we ran it with version B of the code instead of version A? And we added more experiments to our data. And it's slightly risk-free because it's still okay, because you still have your A, which is constantly giving the right data, and you're constantly comparing. It's not like, you release it to 50% of your users and you realize you broke their experience. Because the data analysts, even though they're slightly more difficult than data engineers, in my opinion, they're still much more reasonable than a customer who's paying for something. The last one is actually a lot harder to implement, which is the invariant testing. For those of you who come from domain-driven design, invariance is the rules of the business that have to make sense. The reason why it's slightly more difficult to test is because this is not something only engineers can do. You need the help of data scientists and data analysts to identify when things don't make sense. You have rules in the business that says, for each order, you can only assign 3 or 4 or 5 coupons to it, as an example. And this thing is coming from all sorts of data providers. They don't have the same rules to validate these checks. And you end up with situations where the data doesn't make sense. And you come in like a Tuesday morning and your analyst says, how is this possible? It's physically impossible on the site. But it will happen because you've got coming from different providers. So the invariance testing ensures that we test against yesterday's data or the day before, but it could be something like very similar to what you have on your metrics, on your stats. It's more of a, there's something weird going on here, please have a look at it. For example, you normally make 10,000 sales on a Monday. Next Monday, you just made 4. So it could be that, the credit crunch came in or something, but it could be that people couldn't make orders. And that's something interesting. But your tests will not be able to validate that. Everything ran successfully. So it's more about comparisons between week on week. And people only find this out when you've got really, really smart analysts who are constantly reviewing the data. So we wanted to automate that smartness to constantly check against our data. Another thing we found out is the context switching, really, between moving from web to the data world is backfills. For example, if you have a new field when you're writing web development, it's agreed upon that this new field is now from this day on moving forwards. There's nothing about history. We don't care. It didn't exist. That doesn't apply in the data world, because if we have a new way of calculating a column, or if we have a new way of just showing a graph, we have to backfill it all the way back to all of our history to ensure it's correct. We can't have one version of a field or a column or a value before one day, but not in another. We can't have applying two different formulas. It also breaks our original idempotency rule. So they're very, very important, and it becomes really difficult for your consumers who might not be data related to sort of say, well, I don't care about backfills, just give me the current date. And it might become based on, for example, we had a consumer that had lambdas that would trigger as soon as we write to S3. And then we did a backfill, and then suddenly they realized they were doing millions of rows when they were only doing 10,000 rows. And what's happening is a backfill. Can we disable backfills? No, we can't. So it's a pain that you definitely feel. But absolutely, the biggest pain we felt was with weasels. Weasels are people in the business that you cannot get a straight answer of. So you would tell them something, and you'd ask a question, more importantly, how do you want this thing to behave? And you would get no answer completely. So as an example, because of corrections, you would get a situation where, like, okay, you're talking to your analyst and sort of say, look, we're getting corrections, how do you want to handle them? And they're like, oh, okay, just delete the old records. And say, okay, we can't do that, but we'll somehow do that with snapshots. But we still have the underlying problem that you had a correction. And they're like, well, why is that a problem? And say, well, consider this scenario. You have a product that suddenly, according to your data, is doing really well. So you go up to your executive and you tell them, look, this product's doing really well, let's do some marketing. You do some marketing on it for 4 months, and then suddenly your executive tells you, how's that campaign going? And during those 4 months, the provider actually told you this thing you thought you were doing really well isn't actually doing that well, so here's the right data. So you correct it, and then suddenly your data's changed underneath you. So then you have to basically justify your marketing decision for that product, and you go and query the same data, the same query, the very same query you ran 3 months ago, completely different results. And you're like situation where like you can't justify a decision. So do you want to get the most up-to-date, or do you always want to get the answer you were given originally? And you're like, well, can't you give me the answer correctly all the time? I'm like, well, I can't, right? So what do you want to do? And you end up in a situation where you can't get an answer, and you as a data engineer have to do it to the best of your knowledge, which isn't necessarily what the business wants. And that's one of the biggest pains you feel. So the snapshotting methodology gives you an answer in the sense of you say, this is the most up-to-date, this is the current results up to what we know after corrections. But if you want to query what it was ages ago, then you query it this way, and this is a result you were given originally. But this, in a way itself, is you're forcing to have both ways. You're adding complexity purely because you can't get an answer from the business. So that's one of the most painful things we had to do. We had to handle also schema updates, like I mentioned, where we had a new column here and there. And as long as you add them to the end in CSVs and JSONs, you're good. Actually, JSON, you're still okay. But it has to be at the end purely because of the way you're ingesting this data. Had to add alerting when something fails. Make sure everyone knows. The more you have dashboards, the more visibility you have. This is standard industry practice. But that's all just the pipeline part of ingesting the data. We haven't talked about like the serving layer, which is Presto, which is a way of, it's an engine that allows you to define a schema over flat files in S3, and you're able to query it via SQL. We try to move to things like Athena, but be careful. Don't implement any new AWS service, because Athena had issues implementing with data types like date times. They can do date time, but they can't do dates. And it wasn't a one-to-one match like you expect. But basically, when we had the data in S3, we were able to build recommendations. If we were building recommendations engine left, right, and center, I actually built one based on streams. I was looking at the most interesting things people are doing, ordering products. So I used the ALS, alternate least squares, to basically build something like people who bought this also bought that. So they look at your taste, and they look at what other people's buying, and if you're looking at the same thing, then you're probably like that you guys have the same taste, basically. So I buy 9 things, another person buys 10 things, but my 9 are the same as their 9. I'm probably going to have the same taste as them, so we recommend number 10. So that is the entirety of my talk. Do you have any questions? If not, thank you very much for coming.